Hey everybody, it's Mrs. Meer. I'm going to show you a cyclohexane molecule, and I want to just talk to you about a few things with the molecule and what a ring flip is. So we know that cyclohexane, this cyclic 6-carbon molecule, is actually going to sit more often in what we call the chair conformation. Now remember, conformations are when you can rotate sigma bonds to get different positions. But this is the conformation it sits in most often. Now, why does it sit in this most often? Because it technically has no strain. So as I want you to peek here from the front carbon to the back carbon back here, and if I hold it like this, you should be able to see that it is completely staggered. What happens if I turn and I show you from the front carbon here to the back? Does it look staggered? What about from here? Does it look staggered? So with it being staggered, we don't have any of these hydrogen, which the white and red are supposed to represent hydrogen. None of these hydrogens have any eclipsing. Therefore, there's no torsional strain. And all of the angles are about 109. So there's no angle strain. So we look at this strain-free molecule in the chair position. Now, I do want you to notice that I have two different colors to represent the hydrogens. The 3 sticking straight up and the 3 sticking straight down are white. We call those axial hydrogens because like the axis on the earth goes up and down, we think about. So axial hydrogens, there's 6 axial hydrogens. Now these hydrogens go around the center and they still, this one sticks slightly up, slightly down as I turn it, slightly up, slightly down, but they're still sticking around the center of this ring. And so we call those equatorial, like equator. So equatorial hydrogens, there's 6 of those. So if I asked you how many axial hydrogen, you'd say 6. If I said how many equatorial hydrogen, you'd say 6. But if I asked you how many axial up, you'd say 3. And how many axial down? 3. How many equatorial are up? There's 1 here, 1 here, and 1 back here. How many equatorial are down? The 1 back here, this one, and this one. All right, so we have 3 equatorial up and 3 equatorial down. So at any given point in time, we say there are 6 hydrogen above the ring, 3 axial and 3 equatorial, and 6 hydrogen below the ring, the 3 axial and the 3 equatorial. Now, this molecule will do a ring flip, and it actually can do a ring flip at room temperature. So what happens with a ring flip is we're going to grab a hold of this molecule. I'm going to grab a hold of the top of the chair and the bottom of the chair. And when you do a ring flip, the top goes down and the bottom goes up. I want you to watch the hydrogens that are axial, the white hydrogens that are axial. So as I flip that down and this up, I get my new conformation. Hey, what happened to those white axial hydrogens? Where are they now? Looks like they're all equatorial. Hey, weren't the reds equatorial? And now look at them. What are they? They're all axial. When a ring flip occurs to the other chair conformation, which is just as stable as the first, we notice that everything that's axial becomes equatorial and everything that's equatorial becomes axial, as you can see here again. All right, so to do a ring flip, you grab the head and the foot of the chair and you bring it up and bring it down. And there you go. These are 2 conformations. Now, the one that it does not sit in is called boat. Ugh, that's pretty bad here. Okay, we don't like boat. Why not? Well, we actually have some problems with some torsional strain and some steric strain. So it doesn't sit in the boat, but it does sit in the chair conformation. Okay, that's it.